Alright, so last time we looked at the definition of an enveloping algebra and how it acts across a product. And essentially, it is just the most general form of a Lie bracket such that it splits across, it turns into like this minus swap formula we saw. I mean, you hopefully know what an enveloping algebra is going into this one. So today we're going to look at, first off, we're going to look at the enveloping algebra of a Lie subalgebra. So as always, we're going to let G be a Lie algebra over a ring K. We're going to let H and G be a subalgebra. And sigma and sigma prime, they're, I guess we'll say, the canonical mappings into their enveloping algebras, which we are going to write down as U and V respectively. Then the canonical injection, I'm going to write it fancy, of H into G defines a canonical by definition homomorphism I, but with a tilde on top, of the enveloping algebra of the subalgebra into the main algebra. And this is going to behave with the canonical mappings as you would expect. I'm almost tempted to draw out the image, but I'm not going to. A square. And so the algebra of V under I tilde is generated as you'd expect by 1 and the image of H inside of G. No, the image of H inside of it, of its enveloping algebra. And it says here rather mysteriously that this I tilde is injective in quote-unquote important cases. I'm going to put scare quotes because I'm still not quite sure what they mean by that. If H is not only a subalgebra but an ideal, the left, not two-way, the left ideal of U, because keep in mind U and V are just algebras, that is and this is the left ideal generated by the image of H in its enveloping algebra. Coincides, with the similar right ideal. Once again, I did not read ahead. So it is in fact two-sided. I'm going to call it R. And we check that real quick. For all x in H, x prime in our parent G, sigma of x, sigma prime of x, nope, not sigma prime, sigma of x prime is equal to sigma of x prime, sigma x plus sigma of their Lie bracket by definition. And H is an ideal this by assumption, so this is in H. And so this entire thing is going to be closed, so like in the same area. So quick proposition. Actually, I don't know if it's going to be quick. So we let H in G be an ideal. With P, the map from G to G over H, the canonical homomorphism, and W, the enveloping algebra of this G over H. Then we say that the homomorphism of P tilde from U to W, defined canonically by P, is surjective with a kernel being the ideal, I'm going to call it R, of U, generated by sigma of H. So we have this map G to a quotient of G by H, and so with the maps from G and G over H to their enveloping algebras, that all commutes with this new homomorphism P tilde, and any element generated by the image of H under sigma, which should be getting collapsed, is going to be in the kernel of P tilde, which means it agrees. So let's look over that. We're going to let the map sigma double prime from G over H into W be the canonical map, canonical homomorphism, and this gives us a map, a diagram. We have H, the inclusion map of H into G, and then the quotient map to G over H, and we call the universal algebra of G U, and then V over here W. This canonical map is sigma. This one is sigma prime. This one is sigma double prime. This one is the generator one p tilde, and this is going to, of course, be similarly I tilde. Thus, p tilde is 0 on sigma of h, since if you have elements from h inside of G here, it's going to map to 0 under the quotient, which is then going to map to 0 by sigma double prime, and that has to agree with sigma to p prime, so wherever it ends up has to go to 0. Hence, on R, which as we can recall is the, R is just kernel, so I'm just going to call this R. This is in R. And for our next step, we're going to let phi from U to U over R be the canonical homomorphism again. So then we have that there exists a homomorphism phi from U over R into W such that, and then we have another map here. We have the map from G into G over H. I'm going to draw this one a bit bigger. As before, we have this is P. We have this map sigma from G into its enveloping algebra. And similarly, we have this map sigma double prime into this enveloping algebra. And now we have this new one in the middle here. And we have this map phi with an inverse. And this is the canonical homomorphism. And this we're going to have as theta. And this, of course, such that we can split up that our row, that our p tilde from above is being broken down into phi composed with C. Now the mapping. So first you do sigma from G to U, and then U into U, you divide out R. This is an alpha mapping. And is 0 on H and so defines an alpha mapping theta of G over H into U of R which is the map theta from above that I drew in prematurely. Theta composed with P. So P, yeah, we're going from G to U of R, and these are the two ways of doing it here. And combining these with the stuff from above, we get that phi composed with theta composed with P is equal to phi, make sure this is visibly a phi, composed with psi composed with sigma, which is then equal to sigma double prime composed with P. And this gives us and we see on either side we have on the one side we have phi composed with theta composed with P being equal to sigma double prime composed with P. So everything does commute as we want. Well, I mean, there's still more to check, but. And so there exists a unique, by some proposition they mentioned way before, a map okay, this is not phi inverse. You're going to have to bear with me throughout this. This is a map phi prime. A map phi prime. This is a homomorphism from U, W into U over R. And this is injective. Such that theta is equal to the composition of phi prime and sigma double prime. Then phi prime composed with phi composed with theta is equal to phi prime composed with sigma double prime composed with theta. A lot of this is just chasing the above diagram. And phi composed with phi prime composed with sigma double prime is equal to phi composed with theta equal to sigma double prime. So we get that phi prime composed with phi and phi composed with phi prime are the identity mappings of their domains. And because of this, we see that U over R identified with W under phi. So then the canonical mapping of sigma double prime, which is G over H into W, is identified with theta. So yeah, these two maps at the bottom of the triangle on the right here are these two sets are isomorphic, these two enveloping algebras. Or you know what I'm getting at. And so sigma double prime is identified with theta. that is the mapping of G over H into U over R, which is ultimately derived from sigma. Okay, now the next chapter here is about the opposite algebra, which is something I need to look up real quickly on my phone, because I skipped over that in the beginning. So enveloping algebra of the, and I quote, the opposite algebra. So the opposite Lie algebra of a Lie algebra G is the algebra generated by the anti-isomorphism which sends the bracket to, essentially it just reverses the order. That's what makes it an anti-isomorphism. So essentially, the additive and scalar multiplicative structures on G are the same as its opposite, but the order of the product gets switched. That's the definition for an algebra in general, and that's how it spreads to a Lie algebra. For a general algebra, you just replace the Lie bracket with the standard product. So, put this in parentheses to show it's my text. So we're going to let G be a Lie algebra over a ring K with the opposite Lie algebra being G naught, G to the power of 0. Sounding kind of British there. And canonical mappings of sigma and sigma 0 into their enveloping algebras U and phi. Then sigma is an alpha mapping of G0 into U0 being, where U0 is the opposite of U. So essentially, we need to show that the algebra of the opposite, which we have as V, is the same as the opposite of the algebra, which is UO. Hence, we have a unique injective homomorphism we're going to call it phi from V into UO, which is is an injective homomorphism such that sigma is the composition of phi and its inverse. And the proposition is what you'd expect, that sigma is an isomorphism. And the proof. So it says here there exists a homomorphism sigma phi prime of u into phi naught, which is an injective homomorphism such that sigma naught equals the composition of phi prime and sigma. All right. With phi prime I'm not going to be grammatically correct here. Considered a homomorphism from u naught into v, kind of just taking the opposites of the domain and codomain. Then sigma naught is equal to phi prime composed with phi composed with sigma naught, and sigma can be considered as phi composed with phi prime composed with sigma, hence phi composed with phi prime and vice versa are identity maps, where you would expect them to be. And that is our proof. So sigma, to recap, identifies u naught with a v, and sigma with sigma naught. Thus, the isomorphism theta from G onto G naught as theta of x equals negative x defines an isomorphism theta prime of u to u naught, which is v, this gives theta as an anti-automorphism of u called the principal anti-automorphism. Now, okay, we have I think we have time for one more topic here. Hopefully, we'll find out. That topic is going to be the symmetric algebra of a module. So we're going to let V be a K module. So it says here V can be considered a commutative Lie algebra, and this is obviously going to be unique with the bracket being 0. So what is the enveloping algebra of this commutative Lie bracket? And this is going to be as follows. I'm going to let T be the tensor algebra of V. And I is going to be the two-sided ideal. Ideal of T generated, now if you remember before, it's going to be X tensor Y minus Y tensor X minus the Lie bracket, but because this is the symmetric Lie algebra, the bracket is just 0, so we can just ignore that. So we then form S to be the quotient of T by I, which is called the symmetric algebra. Alright. And so, alright, let's go through some of the properties with no proofs. It's fine by me. So we're going to let T to the N be the set of homogeneous tensors of order n, of course. With this, we see that I is going to be the direct sum of I with T to the N with N at least 2, which gives us S as the direct sum of the canonical images Sn of each Tn. the elements of each Sn are called homogeneous. They're called, they're not, we don't have this as a definition yet. Of degree n. And keep in mind why we start at degree 2, because this is symmetric. Well, looking at the ideal I, the generating terms are all of order 2, and so everything in I has to be at least order 2. Alright, so we're going to call S0 as the scalar multiple of all of k on 1. As always, this is our base element. S1 is identified with V, and as the standard for tensor algebras, s to the n times s to the p is contained within s to the n plus p, as I showed before when I went over tensor algebras. The algebra S here is generated by 1 and S1, which is just our copy of V. And by this property that x tensor y is y tensor x, S is commutative. In an obvious manner. Now, if V is a free K module, I'm not going to cover that right now, what free means, with a basis x lambda, where lambda is indexed by what I only assume is a capital lambda. Our canonical homomorphism f from the polynomial algebra of k with indeterminate x lambda, lambda in V, and the big lambda onto S. This is injective, as always seems to be. And F of indeterminate x lambda gets sent to little x of lambda, and this is actually an isomorphism. Because keep in mind that the tensor algebra, the symmetric algebra, keeps all of the structure of the product aside from the order, and the polynomial ring, the polynomials don't have order in that sense anyways, like they're assuming commutativity, which we have, which is assuming commutativity is how we turn the tensor algebra into the symmetric algebra in the first place. And we can show this more formally by the universal property of S. There exists a map G from S into K x lambda, lambda indexed over big lambda, which has an injective homomorphism with G of small x lambda being big X lambda. And from this we clearly have that G is equal to F inverse, because keep in mind X lambda spans V. Alright, so let S prime n inside Tn be the set of homogeneous, symmetric tensors of order n. If K is actually a field with a char of K equals 0, and then we have that S prime of n and the intersection of I with Tn are actually supplementary inside Tn, of course. Let's write this as a theorem. And for the proof, I'm going to, as before, let x lambda, lambda indexed by big lambda, be a basis of V. Now here's the scary part. We give our indexing set big lambda a total ordering. So we're going to let lambda n be the n-long increasing sequences of big lambda. Now, for such a sequence M of lambda 1 through lambda n, which I guess is just such a sequence of where n is just like, no, n is some n. So m is just the first n never mind. This is just some sequence in lambda n. It takes my brain a while to process these things. And we're going to define y of this sequence to be 1 over the factorial of the number of elements in a sequence times the sum across notation that I cannot read, sigma in the symmetric group of n. Is that the symmetric group or is that the cyclic? I don't know what group that is. I'm guessing it's the symmetric. And then we're taking the tensor of x, lambda is the, So this is just every permutation of the basis elements that's n long. So then, where the basis elements we're looking at are determined by y. And these ym for m in lambda n, that's not an a, that's a big lambda, form a system of generators. Of the K vector space S prime to the n. Their canonical images in Sn form a basis of Sn, so ym for m in big lambda n is a basis of a supplementary subspace of I intersection of Tn in Tn. So essentially this is collecting every way that a set of n vectors can be like not symmetric, and that's a complement in some form. Thus, when K is a field of character 0, the restriction of the canonical map from the map is from Tn to Sn, and we're restricting it to S prime n is an isomorphism of S prime n to Sn and so has an inverse. The inverse isomorphisms for each such n define a canonical isomorphism of S onto the space S prime equal to the sum of each such S prime n of symmetric tensors. And I think we finally have enough content to call it there for an episode. That's 50 minutes. next time we got plenty more enveloping algebra talk to go. How far are we through? Like so. I don't know. I think we're not quite halfway through, like based on our current pace. I think there's going to be another 3 or 4 episodes based on how I pace it, just of enveloping algebra. So most of tomorrow's is going to be more enveloping algebra talk.